banking, financial services, insurance, uh, networking, cellular, telecom, healthcare, and other industries. And he is also, in addition to being a developer, a great mentor to other developers. He delivered several highly rated talks on different topics, including today's topic, which is debugging, which is a really, really interesting topic for any developer because, you can't debug enough, right? So, even if you're a very senior programmer at your level, you always get the feeling that no matter how rigorous you are in your debugging, you still, sometimes leave some things and that will, create problems in production and stuff like that. So the art of debugging is something that people only pick up through experience, but this course tries to, sort of give the middle to junior level developers some sort of an advantage in quickly understanding some of these debugging techniques that will help you become a better programmer. So with that, I will now step aside and I will have Shai take over and begin the session. Shai, thanks a lot for taking the time out to join us today. Over to you.
Thank you for the great introduction and for inviting me. Just one tiny correction, not art of debugging, science of debugging, because there is a lot of science behind it. And unfortunately, not enough of us are familiar with it. Now, before I actually start my presentation, which I'm going to work on sharing my screen here, before I get to that, I want to say a couple of things about I want to say a couple of things about the presentation itself. This presentation is written mostly for Java developers using IntelliJ IDEA. Now, it's still applicable to developers in pretty much any language and any IDE, but making it generic enough would essentially void it of any value. So you can apply most of the techniques that you have here, have slightly different names sometimes, but work for Visual Studio, for Eclipse, for other languages with JetBrains IDEs and with other IDEs, not so much with Visual Studio Code, which is overly simplistic in its debugging, but Visual Studio is great. So these ideas are generic, even though I express them in Java. So otherwise I'd take forever to finish the talk. So let's get started. 25 years ago, I got lucky. I was sure I was a great programmer. And then I had a debugging session with a senior developer, and I was completely floored by the way he wielded the debugger. He used features and techniques that I was totally unaware of. I had no idea that you could do these sorts of things. We don't learn debugging in university because they don't teach these things because they can't test them. A tool we spend so much time inside on our day-to-day job is essentially left as a take-home exercise. I was lucky to get a glimpse of competence that made me study this tool and the surrounding process. Hopefully, I can pass some of that luck on to you. As Shashi introduced me earlier, a few things about me that we mentioned before. I founded a couple of companies, wrote a few books. You can contact me over my socials that you can see here, and follow me on Mastodon, Twitter, LinkedIn, YouTube, especially where I have lots of videos related to Java debugging and everything related to that. As I said, I published a few books. This is my third book from A Press that talks about debugging. The entire talk today is essentially some of the first chapter of the book. It has 14 chapters, so there's a lot to talk about when it comes to debugging. I also have an upcoming book from BPB called that will talk about Java 8 to Java 21 and everything that's new in the interim there. This talk is divided into 4 acts. In the first one, which I already started, I'll discuss about personal pet peeve of mine about debugging. Because hopefully you all know the basics of what debugging is. I assume everyone here knows how to set a breakpoint, step over it, look at a watch expression. This talk goes a bit deeper than that. But first, I want to start with that 3-minute rant. Why do people hate debugging? There's an antagonism towards debugging and debuggers. In some cases, that makes sense. I used to debug on embedded and mobile devices, and back in the day, that was a terrible experience. But still, most of us treat debugging like taking out the trash. We hold our nose and run, trying not to smell it. We don't develop debugging skills because we don't want to debug. We want our code to work. We treat this crucial part of our job as punishment. I think the reason is that we feel stupid when we find that the bug is stupid. In most cases, it's something dumb that we did. The debugger shows us and we feel like idiots. No one likes to feel like an idiot, and the debugger is there pointing at the bug. And I guess most people think of it like that. Personally, I don't like to think of it like Nelson. There's a universal gesture of debugging. When I show it in my talks, everyone agrees this means debugging. I think of debugging as a Zen practice, as a way to humble myself. People tell us how smart we are all the time for doing this type of work. It's a very grounding experience to know that I'm an idiot. So I'm thankful for debugging sessions. They keep me grounded. I think managers and thought leaders in our industry would greatly benefit from sessions of debugging and connect more to their inner self and inner humility. In fact, one of the chapters in my book talks about using debuggers as a learning tool. When I open a new code base and I need to understand what's going on, just reading a huge project isn't practical. But spending a few hours in a debugger can teach me everything I need to know. Debuggers aren't something you should reach only when you experience a bug. That's a mistake. You should reach for debugger for everything. When you want to understand, when you want to learn, when you want to verify, when you want to do something related to a code change, you instantly test it within the debugger. You don't necessarily need to first write the unit test and do that, but rather test through the debugger and then write the unit test based on the things in the debugger. Let's go into concrete debugging examples, specifically about control flow. We'll cover a lot of features very quickly. Some you might know and some you might not. I won't go into basics though. I assume everyone here knows the basics of using IntelliJ IDEA and a debugger. If you have a question, please post it while I'm talking, and Shashi will hopefully ask it in voice, so I'll hear it during the talk. Force return lets us return immediately from a method and potentially return a different result from the method. So when we're experiencing a problem, we can return fake data from a specific method to simulate a problematic condition. Unlike step out, we return from this point while skipping the rest of the method. We type in the return value and the rest of the code won't execute. This lets us change the control flow of the app. We can return different results or skip problematic code to see what happens next. Imagine a case of a hard-to-reproduce bug. This means we can simulate the conditions that can trigger that bug. But this gets better. We can actually move the current instruction pointer to a different position in the method. In IntelliJ, we need to install the Jump to Line plugin for this to work. This is an amazing feature and remarkably underutilized. I know people don't know about this feature because the install numbers for this plugin are sadly very low. Once the plugin is installed, we can drag the arrow on the left to bring execution to a new location. If you saw a bug, just drag the execution back and reproduce it. We can skip over code that's failing, etc. Imagine building a unit test. Just drag the execution point back and forth and tune the variables you passed into the method. That way you can get a sense of the right arguments you need to pass to get good coverage. It's the ultimate do-over button, and you don't need to stop, recompile, or anything like that. A watch point is a breakpoint we can place on a field. This is pretty standard, but a surprising number of people aren't aware of this capability. We can place a watch point on a field, which will stop every time the value of the field changes. This is a remarkably cool way to catch a case where some code mutates a variable. We can tune this so it stops not just for changes to the field, but also for reading the value of the field, or only for reading the value of the field. Trace points are probably the most important feature of a debugger that developers don't use enough. Trace points are often called log points. They're a special type of breakpoint that doesn't break. They don't stop the execution and just log to the console. You can add a trace point by shift-clicking on the gutter. Notice I can write any valid expression here, either a string, variable, or method invocation. This is effectively a log I can add in runtime without restarting my app. It has full access to variables and everything. It's print-line debugging without the risk of accidentally committing the debugging code to Git. It's fantastic. Notice that you can set a trace point by unchecking the suspend checkbox you see here. A breakpoint breaks by default, which means all threads are suspended. A trace point lets you disable that behavior. Notice you can also create a breakpoint that only suspends a single thread and not all of them, but that's a different subject. Logging is debugging, and trace points are exactly that. If you have race conditions, which are normally very hard to debug with regular breakpoints, a trace point is a perfect tool to track those. Notice that trace point is like system printline debugging, and logging is a bit different because printline debugging is ephemeral. It's something that vanishes, so it's similar to trace points. Logging is a form of debugging that's persistent. That's something you want to keep in the code, and it's different in that sense. Method breakpoints are similar to what we think of as line breakpoints, but they have some important distinctions. Method breakpoints are normally emulated by the IDE. It just uses line breakpoints to simulate method breakpoints, but there's a huge use case for real method breakpoints. Say we want to break on all the methods starting with the letters I and S and classes whose names start with prime. This might seem far-fetched, but is actually a useful use case. If you have an abstract base class whose subclasses follow a naming convention and they have many related methods, you want to track everything, you can do that using this approach. Notice you can also use trace points here and get very deep logging, such as a log or a stack trace every time a specific set of APIs is invoked. Breaking on all exceptions or on some problematic exceptions is terrible. The IDE stops every second. I'll enable breaking on any exception to show this. People don't do that, and the reason is we hit it a lot. It becomes useless for real-life applications like this. We can solve this with the catch class filter. We can just exclude all the exceptions caught by the Java API. And this filters out these exceptions that are handled in the JDK. Exceptions in my application will stop here despite that. It's amazing that this isn't the IDE default. Without it, this feature is useless. This is a really important feature to keep running all the time. Without this, you sometimes get printouts of log errors in the IDE console, and you don't see them because you're debugging or you're doing something else. So you don't even know that an exception happened. If catch all exceptions is enabled, then you will see these uncaught exceptions or caught exceptions that you should have noticed. And you'll instantly see them in the IDE and you'll be able to resolve them. So it's very important to keep that checked. Next, we'll discuss debugging of asynchronous code. One of the reasons I love Java is that it's so darn easy to debug. We just step into a method and we can move between threads. That's easy. But some of that is habit. In recent years, the approach of using async await and similar asynchronous techniques gained traction even in the Java realm. Debuggers kept up with this and let us see glued together stack traces. Let's dig deeper. Here we have a standard async example from JetBrains that uses a list of tasks and just sends them to the executor to perform on a separate thread. Each task sleeps and prints a random number. Nothing to write home about as far as demos go. This is pretty trivial. Here's where things get interesting. As you can see, there's a line that separates the async stack from the current stack on the top. The IDE detected the invocation of a separate thread and kept the stack trace on one side. Then, when it needed the information, it took the stack trace from before and glued it to the bottom. The lower part of the stack trace is from the main thread, and the top portion from the executor thread. Notice that this works seamlessly with swing, with executors, with string async annotation, etc. That's very cool. How does this work under the hood? And what do you do if you have custom code that's asynchronous? The IDE works by saving the stack trace in places where we know an asynchronous operation is happening, and then placing it later on when we needed it. How does it connect the right traces? It uses variable values. In this demo, I created a simple listener interface. You'll notice it has no asynchronous elements in the stack trace. By adding the async schedule and async executor annotations, I can determine the point where an async code might launch, which is the schedule marker. I can place it on a variable to indicate the variable I want to use to look up the right stack trace. This is literally a hash map lookup. I do the same thing with execute and get custom async stack trace. I can put annotations on a method and the current object will be used instead as the lookup key. Seeing the values and the current state is one of the most important tasks of a debugger. In this section, we try to get deeper insight into the debugger feature, the watch. The data we see as we debug is how we reach the conclusions. A lot of the times, it's an absolute mess. I assume you all know how to add an expression to the watch. I even assume that you know you can add watch expressions directly to the editor body in IntelliJ. I don't cover that here. It's cool, but not as groundbreaking as renderers. One of the most annoying things to me is when I return from a method and have no idea what the return value was. This can happen because the developer didn't define a variable and just used a return value as an argument to an internal API, which I can step into or even use it as part of an equation. Please, developers, don't do that. It makes code hard to debug. But this feature solves that problem, and amazingly, it's off by default, because this is a very common problem. Luckily, the IDE has an option called show method return value, and it saves the value for us so we can inspect it right away. Once I check it, you can see the return value of is prime appearing in the watch area. Let's zoom in a bit. Right here in it is the fully qualified name of the method we returned from, and the value returned from that method. If there's one killer feature you will get from this talk, it's this, object marking. It's also one of the harder concepts to grasp in my talk. Object marking lets us declare a new static variable in runtime and store that value of an expression into it without restarting or recompiling the code. To explain object marking, let's add a watch of the current thread method. We right-click this watch entry and create a marker object. Object marking lets us give a global name to a specific object so we can later use that name even when the object isn't in scope. That means I can later check if current thread is equal to the myThread variable and get a proper result. What this means isn't that the myThread label is now just an alias to get current thread. It isn't. It copied the value that get current thread returned right now. And now we have the result of get current thread, which is currently the same, and my thread label, object marker, which is also the same, but it's a copy. So that means that even if I'm out of the scope of the method, that value will remain the same. It's like back in the past, we used to write pointer values on a piece of paper and constantly compare them to the pointer value I saw in the IDE to see, wait a moment, is this the same object as I have right here? So with marker objects, we can automate this, but not just automate it in the level of looking it up in the watch area. We can automate it in conditions. This is immensely useful when dealing with many objects. In this case, I can literally check if the method will be hit with the same thread. I can use it to compare any objects instead of writing their pointers on a piece of paper. I often use this with APIs like JPA, where we might sometimes have two object instances with the same identity, but different pointers. This is really hard to detect. But in this case, I can just mark one object and then I can instantly compare it with conditional code like this. In this case, I'm taking the previous value of thread.currentThread and checking if it's still the same in the conditional breakpoint. And if it's not, if this method is now entered with a different thread, the breakpoint will hit. I used to love game cheats as a kid. And this specific feature makes me feel like it's a cheat mode in debugging. We can show all the objects of a given type. By right-clicking a thread and selecting Show Thread Objects, we can see all the thread objects in the virtual machine. We can even do that on a string array and show all the string arrays in the VM. Notice that in both cases, we see internal objects from the VM. We even saw the JIT compiler thread. This is a remarkably useful feature, especially when tracking memory issues. Notice there's a filter bar at the top, and you can search all of these objects to find something using a Java expression. And this means I can find an arbitrary object and see where a specific piece of data is coming from potentially. This is something that was standing right in front of my eyes, and I didn't see it for ages. Filtering is a very powerful feature when we have code that views arrays or collections. We can just filter the content using an expression and reduce the noise significantly. In this case, I have 4 elements in the pet clinic demo. I narrow them down by testing against the pet ID. Notice I use this to represent the current element in the list. This is very versatile. If we have a list of names, we can filter it so we can only see applicable names. Notice that the array, the list that I have here below, skips numbers in the offsets because of the filter. So you can instantly see how many elements were filtered in between when viewing the array or list. It's very useful for that. Streams in Java 8 are constructs inspired by functional programming that let us process a stream of elements. They're pretty cool, but one of the problems in them is that they are notoriously hard to debug. IntelliJ ships with a stream debugger that you can find in this button that I'm pointing at with the mouse. When you press it, you need to be positioned on a stream in the debugger. As you can see, I am in the line above. Notice that if you're not positioned on a stream, you might not actually see this button at all. It might be completely hidden. Pressing the button launches the stream debugger. On the top, you can see the stages of the stream expression. Notice that as I traverse through the stages of the expression, the objects change and draw a line between their original mapping to the new one. Initially, the list was of visits, and now we see the conversion to the pets in each visit. Since the final stage is a set, we will only get one instance of each pet. That isn't shown here. The advantage here is that you can see the entire process in a single view that you can take back and forth. unlike a loop, which you normally debug by stepping in the debugger, the view here is a bit more complete and highly inspired by time travel debugging, which is a complete subject in its own right. Rendering is one of the features that we just don't expect. We think of watch expressions as a fixed thing, but when we're debugging a huge system, things can become tedious. A debugger can only show what it knows about. And for the most part, it's just guessing. With renderers, we can determine how an element is displayed in the watch, but we can go much further with renderers. To get started, we can customize the renderer through the right-click menu here. For the most basic customizations, we can toggle and enable multiple features with this dialog. Then press apply to instantly see them in the variable view. I can see the declared type of the field. We can include fully qualified names for class files. We can see the static field values. We can include hex values for primitives by default, and just so much more. Renderers slow down the program execution. So if you feel that step over is slow, just mute them like this. Then you can see individual values for renderers by clicking the specific item. Let's take this up a notch. We have a repository instance, and the visit repository variable below doesn't provide valuable information. Now, those of you who don't come from Java might find this odd. Repository is a concept from string data, which represents something similar to a table in database programming. It's essentially an abstraction similar to that, not exactly, but gross oversimplification. So what I would like to see normally is the number of entities in the table, but what I saw was gibberish. I saw just the value of toString listed there. We can now add a renderer that applies to JPA repository, which is the base interface of this instance. Then we just write the expression to represent the rendering right here. We show the number of elements in the repository using the count method. This produces an SQL count call and actually shows the number 4 in this case, because I have 4 rows in the table. Notice I don't provide an object instance. The IDE automatically runs this in the context of the object. You can use this to represent the rendered object, but you don't have to. You can run this on demand, which makes sense for expensive operations. This is like the mute, only on the individual renderer. Look at the visit repository variable preview and see the value, how it instantly adapted to the changes. Now, if you come from Java, you might say, wait a moment, that's just toString. Why not write a toString method? And you'd be 100% correct, only you'd be a bit wrong as well. Because a toString method is something that goes into production. So if you accidentally send this object to the log, then every time you print that object to the log, you will do a select count on the database. You don't want to do that. If some tool does a toString on the object for you, suddenly you get this amazing set of performance problems and database problems. You don't want to do a select count in a toString. And to add to that, you can't actually do that because this specific object is implemented by string. So you can't physically override its toString method. The only way to do this is with a renderer, but it gets much better. The view repository is rendered with the right string containing the element count, but it isn't properly expandable. We can execute the find_all method on the expansion, and the responses will appear below the object like any other array. This does a select star and brings all the entities from the table. To make this even cooler, I define an expression that indicates if the data is expandable using the count method. And now we can look at all of the data as if it was an array, and it's very inefficient, but it only happens while we're debugging. So the problem of efficiency isn't really relevant here. It won't harm production. Let's talk a bit more about custom rendering. You'll notice that everything looks exactly the same. the numbering, the list of entities, etc. But when we open the list of renderers, it's blank. There are no renderers. How does this suddenly work without a renderer? What's going on? We use code annotations to represent the renderer. This way, you can commit the renderer to the project repository, and you don't need to configure individual IDE instances. This is pretty simple. We add a dependency on the JetBrains annotation library into the POM. Since these are annotations, if you're not a Java person, they have no impact. On other platforms, JetBrains has this as comments and things like that. Annotations are a source level, compiler level feature. They don't impact production overhead. We add an import to the renderer. When we scroll down, we added a simple render annotation code. Notice this is pretty much the code I typed in the dialog, but this time it's used in an annotation, so my entire team can benefit from the improved view of repository objects. If you have a library that's geared towards developers, and third-party developers, etc., then you can add things like async support, annotations for renderers and things like that to make the debugging experience for those third parties or for those teammates much easier without them having to configure their environments to add these sort of things. They don't need to know about renderers to benefit from them. When we think about memory debugging, we usually think about profilers, which do have some functionality for that. But the standard debugger has some amazing capabilities. Memory debugging is a very expensive tool, so it's off by default. When you don't need it, disable it so your debugging performance won't suffer. We start by launching the memory view from the IDE UI menu. Notice that the memory view is empty by default, even after we launch it. This keeps the IDE responsive. In order to see the actual objects in RAM, we need to click the load link in the center. Once loaded, we can see the instance count for every object. This helps us get a sense of what exactly is taking up RAM. But that's only part of the story. When we step over, there are allocations happening in methods we invoked and possibly in other threads. We can see the difference between the current point and the one before when we look at the diff column. We can double-click an individual entry and see all the instances of the given object, which is a remarkably powerful feature that we discussed previously to some degree. But this is tedious. I have a fast machine with lots of RAM. I can just enable update loaded classes on debugger stop, and I will no longer need to press load explicitly. Only do that if your machine is a monster. Track new instance lets us explicitly track the individual allocations that are going on between 2 points. We can enable that by right-clicking any non-array object and enabling this option. Once enabled, we see a small watch sign next to the tracked object. But there's a lot more involved. As we continue the execution, I can now see only the objects allocated specifically in this diff and can understand exactly what happened in terms of RAM between the previous point where the application stopped and the current point. That means I can step over a method and see the objects allocated in that specific method only and not through the entire application. I can also click an individual object and see the stack trace that triggered it all the way up to the literal call to new. I can see exactly how a memory leak happened from the start all the way up to the actual allocation. That's spectacular. Threading issues are notoriously hard to debug, but this reputation isn't necessarily always justified. Once you understand the basics, you'll find that most threading issues are pretty similar. Let's start with the basics of thread debugging. In the stack frame, we can look at all the current threads in the combo box above the stack frame. We can toggle the currently selected thread and see the stack for that thread and the thread status. Notice that here we chose to suspend all threads on this breakpoint. If the threads were running, we wouldn't be able to see their stack as it's constantly changing. We can enable the thread view in the right-hand side pull-down menu to see more. As you can see, viewing the stack is far more convenient in this state when working with many threads. Furthermore, we can customize this view even more by going into the Customize Thread view and enabling additional options. The thread groups option is probably the most obvious change, as it arranges all the threads based on their groups and provides pretty deep view of the hierarchy. Since most frameworks arrange their threads based on categories in convenient groups, this is often very useful when debugging many threads. Other than that, we can show additional information such as the file name, line number, class name, argument types. I personally like showing everything, but this does create a somewhat noisy view that might not be as helpful. Now that we switched to the grouping, we can see the hierarchy of the threads. This mode is a bit of a double-edged sword, since you might miss out on an important thread in this case, but if you have a lot of threads in a specific group, it might be the only way you can possibly work. The first step of debugging a race condition is a method breakpoint. I know what I said about them, but in this case, I need it. Notice the return statement in this method includes a lot of code. If I place a breakpoint on the last line, it will happen before the code executes, and my coverage won't include that part. I only use it for the exit portion because if I used it for both, I'd have no way to distinguish between exit and enter events. I make this trace point by unchecking the suspend option, and then I log the name of the thread. I now do the exact same thing for a line breakpoint on the first line of the method. A line breakpoint is fine since entry to the method makes sense here. I change the label and make it also into a trace point instead of a breakpoint. Now we look at the console. I copy the name of the thread from the first printout in the console and add a condition to reduce the noise. If there is a race condition, there must be at least one other thread, right? So let's remove one thread to be sure. Going down the list, it's obvious that multiple threads enter the code. That means there's a risk of a race condition. Now it means I need to read the logs and see if an enter for one thread happens before the exit of another thread. This is a bit of work, but is doable. The next step is debugging deadlocks. Here we have two threads, each is waiting on a monitor held by the other thread. This is a trivial deadlock, but debugging this sort of deadlock is trivial even in more complex cases. Notice the bottom two threads have a monitor status. This means they're waiting on a lock and can continue until it's released. Typically, you'd see this in Java as a thread is waiting on a synchronized block. You can expand these threads and see what's going on and which monitor is held by each thread. If you're able to reproduce a deadlock on a race in the debugger, they are both simple to fix. For the final act, we'll talk about remote debugging, which I hope most of you know already. I'll try to cover a niche of remote debugging, which isn't as well known, and discuss some of the core problems with it. It's an amazing and powerful tool, but it also has significant weaknesses. The first and foremost is security. The Java debug wire protocol is the actual set of commands that we go through for wire debugging in Java and JVM languages. We usually call it JDWP for short. This protocol enables remote debugging since it can be run in a network mode. The problem is that this is very susceptible to attack. One of the simplest things we can do to secure JDWP is to tunnel. Tunneling means opening a secure connection between this machine and the server. We connect to a remote host, and then all the traffic on the remote port is tunneled to the local machine and vice versa. Both machines think they're connecting to the local host, but in reality, they connect to the remote machine. Notice that in this sample, I used port 9000 to mislead hackers scanning port 5005, although it wouldn't matter because it's tunneled through SSH. We can do the exact same thing with Kubernetes using the port forward command. to redirect a remote JDWP connection to localhost. Port forwarding opens a secure tunnel between your machine and the remote machine on the given port. So when I connect to localhost on the forwarded port, it seamlessly and securely connects to the remote machine. Once we do that, I can just open IntelliJ IDEA and add a run configuration for remote debugging, which already exists and is pre-configured with the defaults such as port 5005. I just give the new run configuration a name, and we're ready to go with debugging the app. Notice I'm debugging on localhost, even though my pod is remote. That's because I'm port forwarding everything. Lost my voice there for a second. I make sure the right run configuration is selected, which it is. We can now just press debug to instantly connect to the running process. Once that is done, this feels and acts like any debugger instance launched from within the IDE. I can set a breakpoint and step over and get this wonderful debug GUI I'm pretty much used to. This is perfect, right? The first problem is the need to kill the process and then rerun it with debugging enabled. This is insane. We can't kill a running server process just like that. But the alternative is worse. Running with debug always enabled is a recipe for disaster. We can't have that. It's not a security risk in the same way that leaving your door wide open with an itemized list of your valuables sorted by worth and location right in the entrance isn't a security risk. It's an open invitation for hackers. Even if I tunnel everything via the port or SSH, it's still a huge security risk since debuggers weren't built for that. Debuggers themselves weren't built for that either. The most basic unit we work with, the breakpoint, stops when we hit it. That isn't practical when we're debugging production. Imagine your execution thread suddenly stopping in the middle. There are solutions for that, such as trace points, but they are awkward to use, and you can accidentally add a breakpoint just by clicking in the wrong place. Debuggers are slow. They fetch a lot of data for the watch. They significantly slow execution and often stop the world. We can't place an overhead like that on a production server, and debuggers are much slower when they work remotely. When we talk about security, we often look to risks outside of the organization. 60% of breaches are from the inside. A disgruntled employee, embezzlement, etc. In such situations, a debugger is a goldmine for a malicious employee. Such a person can place a breakpoint on the part of the code that takes login and password details, then siphon away the user credentials. They can even set permissions on their own account in the debugger and give themselves full access to the platform. As a kid, I used debuggers to hack into systems. They are the best possible tools for hackers. They are wonderful, but they were not designed for production. If we use them, it needs to be surgical and under very strict control. Finally, there's the issue of scale. We need to know where to debug. In a simple solution with one server, we can just place a breakpoint there, but this is rarely the case. We can sometimes segregate a system strictly for debugging purposes, and with some creative load balancer configuration, redirect the problematic user to that machine. That isn't always practical. Ideally, we want to debug at scale. We might have 1,000 server processes running concurrently. We might have to debug them all at once. This isn't doable in a debugger. While remote debugging is wonderful, we shouldn't use it in production for these reasons. There are a lot of alternatives such as observability tooling, developer observability, etc. I get into them in my book, course, and some of the other lectures that I've given in the past. And with that, we're heading for the summary. In closing, I'd like to review some of the things we discussed today. I hear people say, oh, I debug with print or logs. To me, that sounds like the person is publicly declaring they don't know what's a trace point. So please don't say, oh, print debugging. Marker objects, renders, and many of the features we discussed here are amazing. Please use them. Memory debugging, field watch points, etc. can change your debugging like nothing else. Exception breakpoints can be useful with the right filters. Have them enabled all the time and never miss an exception again by just accidentally clicking restart. Use renders and similar tools to see variables you're working with. It will boost your productivity and change the way you and your team debug. Please be careful when debugging remotely. Never do that in production. That's why we have observability. And thanks for bearing with me. I hope you enjoyed the presentation. Please feel free to ask any questions, and also feel free to write to me and on socials and everything. Check out my books and YouTube and everything. And thank you all.
Hey, thanks a lot, Shai. A brilliant presentation.
Thank you.
Like I said, debugging seems like such a commonplace thing, but then, there's a lot in it that most people don't know. In a way that makes programmers productive. And this is really brilliant. And I personally enjoyed the things on the ports because the tendency is for developers to ask for a lot of these ports to be open. So you don't debug that. And then when you're in production, all sorts of crazy things happen. So
yeah.
So that's like a great walkthrough there on debugging on ports, and also especially around that advice, right? That most people, I've seen this happen quite a few times where people tend to forget to switch off debugging in a production environment, and again, that's when you expose things that you shouldn't be exposing, and then you run into all sorts of problems. Again, great advice. Thanks a lot for doing this. And for everybody who joined, I highly recommend Practical Debugging at Scale, published by the apress.com. Just go ahead, get the book, read that. And then, what we covered is just some extracts from chapter 1. You'd have like a whole lot there that's not covered as part of this talk. So highly recommend you to kind of check that book out. So some questions that I have, Shai, that I've sort of compiled for you. So one is, how do we debug in production for issues that we can't reproduce in staging? I think you covered this a little bit, but yeah, the question is.
No, I didn't really cover it. This is a huge subject. There's the entire section of the book is dedicated to that. Actually, the book is divided into 3 parts. The first one is the tooling and the environments, the theory and all of the local stuff. The second part is about production and observability and all of that. And the third part is about real world, taking everything we learned into the real world. So this is an entire section of the book, not just a chapter. I'll try to sum it up in just general concepts. It's observability, and there's several tools for observability. And this includes also proper logging and things like that, but obviously tracing, metrics, and everything related to that, and developer observability, which is a new rising field in this subject, in this area. But it's also being prepared. There's a Hebrew saying that it's easy in practice. The practice is difficult, the battle is easy. And I think testing and logging and things like that are, the practice, because I usually say logging is precognitive debugging. And doing that right will change the way that your production works and the type of issues that you deal with in production. You still need a full observability stack, so you will be able to deal with the production bugs. And usually when we talk production bugs, if you have bad tooling, then you have very few production bugs, because first of all, you don't notice them. And second of all, you stop defining things as production issues. So you only look at crashes as production issues, which usually when I say production bugs, people automatically go to that. But to me, production bugs are things like a user is complaining that he isn't seeing all of his teammates in the system, stuff like that. And that's happening in production, and I can't reproduce it locally. And these sorts of bugs, which are like 95, 98% of the bugs, are really, really hard to debug in production without proper observability, without setting everything correctly in advance, without real precognitive debugging. And you end up with a sort of, I call it the CI/CD cycle of death, where you keep adding logs or things like that, or keep making wild goose chase attempts. Now, all of this also goes back to theory of debugging, because lots of times when we face a bug, whether it's local or in production, we sort of start guessing. And this is something that's one of the things I had a problem with when you initially said about the art of debugging, because debugging isn't about guessing. There's a methodology, but most of us, because we didn't learn this methodology in university, we end up guessing. We end up looking at it as a sort of an art, but there's a process to narrow down a bug, and that includes two forms of verification. Now, in production, to get observability right, you need to be able to prove any assertion with two different forms. And let me clarify that. Let's say I have a problem of some data not appearing. That might be caused because the data isn't coming from the database. So I'm making an assertion that the data is coming properly from the database. That's the first point. I'm narrowing the bug, that the bug isn't happening in the database. And that's the basis of the theory. Now, normally, one of the mistakes people do is that they make a check. They do a select query on the database and they say, okay, the database returned the value, we're good. But that's one way of verifying it and of looking at the select output and everything. Usually you need two ways to verify it. And you usually want another way that also checks it in a way that's more similar to the way the application works and not externally. And why two? Because one of the ways might mislead you and might provide, might include a problem. And so you'll keep looking in the wrong place. By using two ways of verification, similarly, to double booking, to an accounting system, by using two different verification ways, you can prove something. Now, why only two? Why not 3, 4, or infinite? So when you have too many ways of getting the same data, then your system is overly observed. Then you have too much information. And this is expensive. You store too much information, you slow down the system because you're observing it. And you're also getting confused because you have too many ways of solving the same problem. All of these aren't good things. So the solution is to have two ways to observe anything. And that way you can slowly narrow down the bug by sort of rounding it up, by verifying your assumptions around it. And if something is tricky, this is anecdotal. This is hard to prove it theoretically. I don't know a way to do that. But it's anecdotal for all the decades I've been programming. If it's tricky, then it's one of your assumptions is wrong, always. And you need to go over your assumptions and double verify each one of them.
Right. Yeah, that helps. That helps. And the other question is, this developer who's been asked by his manager to implement what he called preemptive debugging. So he just wants to know what would be the top two things where he can start, because he hasn't done it ever.
So preemptive debugging, I use it as a term to describe observability and mostly logging, right? Because when we log, we lots of times don't have a standard for what we want to put in the log. So one developer would have lots of logging all over the place and have them in completely different mixed up levels, and another person would do something else. And this would all go into the code, and we'd look at the log and see there's something that's a complete mess. The thing is that every company needs, I have a video and a post about it, and also in the book, about logging best practices, which talks about how a log should be written in a way that facilitates future debugging, which is why we write the log. We don't write the log for the sake of logging. we write it for the sake of resolving potential problems. And we need a company-specific standard that describes how our company expects the log to look. We need a review process of the physical log when things are working, not when they're failing. Some of our best bugs we found when we were looking at a log of a build that succeeded, not one that failed, because there's things printed in the log that don't make sense sometimes, but you won't see it because it all passed. And the ability to have a baseline, to look at a log that's good, to look at observability information and dashboards that are good, and have that sort of baseline. So when production does fail, you look, oh, this number or this printout doesn't make sense, because you'd instantly see it, because your pattern recognition in your mind will notice that stuff that shouldn't have been there, that isn't standard. That's really important. So I suggest checking out that video, that blog post about called Logging Best Practices. I also had another lecture about that recently. So debugagent.com, you can check out that lecture. It's essentially a template that you can use in your organization to write sort of tune it to your needs, not take my words or my opinions. Take the ones that match your particular needs, but be consistent, because the code review process, when you decide to merge something into the code, doesn't really review logs properly. You know, one reviewer might say, oh, this logging is good. Another one will say you didn't log enough. Another one will say you logged too much. But we need a balance, and we need a standard per company that a reviewer can refer to and say, oh, look, this code passes code review because there's enough logging, or the right amount of logging, and it's at the correct log level, and it logs the right information. And all of that is covered there. It's
great. Yeah. Thank you for that. So I think that's where we'll stop the Q&A. But again, once again, thanks a lot, Shai, for a great session.
Thank you.
Very, very helpful, and very useful for a lot of our participants. And a recorded version of this will be up on our site very soon. And this will really help future learners also on the platform. Thanks for doing this with us today. And we hope to bring you back for another session soon.
Hopefully too.
Yeah.
Have a nice day.
Bye-bye.